In the last lecture, we saw that the ANOVA test could be used to generate identical results as a simple linear regression. In a simple linear regression, we use the algebra we derived about inference on the t distribution on the null hypothesis that the slope equals 0. And in the previous lecture, we saw that we could get identical inference by comparing a complex and simple model where the difference between the two models was that the slope equals 0. We were interested in developing the ANOVA framework, even though we already had the regression framework, because the ANOVA framework is extremely flexible and allows us to capture arbitrarily complex models and perform inference in any way that we want. So we're going to over the next few lectures, build increasingly complex ANOVA models. And we'll start by showing that the ANOVA, in this lecture, we'll start by showing that the ANOVA model can be used to generate the same inference as a simple two-sample t-test. So remember the two-sample t-test. So consider that we have two categories, let's just call them A and B, with certain amounts of data. This could be, the mice on drug A versus the mice on drug B, something about the mice, their weight or lifespan or whatever. We've seen that when we have two vectors in R, we can say t-test AB, and we get a p-value. Notice that in this case, I'm using the equal variance t-test, not the default t-test that drops the assumption of equal variance. And that's because when we build these ANOVA models, we can recapture the statistics of the t-test. But the ANOVA models have a disadvantage with respect to simple t-test in that this assumption of equal variance creeps back in. And this assumption of equal variance among different conditions is going to be with us basically for the rest of the semester. So we pick it up here again, and we essentially never lose it. And we'll talk about ways to look at how to measure whether a particular data set meets this assumption of equal variance. So simple t-test, as in a few lectures ago, a data set and produces some p-value, in this case 0.02486. So to do this using the ANOVA framework instead of the simple t-test framework, we make one. So instead of having our vector be two data, or our data be in two vectors, we combine them into one vector, and then we make another category vector, right? So the first 4 data points are category A, and the last 5 are category B. We here explicitly tell R that these are factors. So these are non-numeric data, they're categorical data. So you're on drug A or you're on drug B, or you have a Ford or a Mustang, or I guess a Ford or a Honda, or a Toyota. Right? The categorical variables that are not ordered is what R means by factors. R would have figured out that these were factors just because they're strings, but here we explicitly say that they're factors. Then I say my linear model equals linear model, my data, categories, right? So the y data is the data, the categories is this factor, x equals true. When we perform an ANOVA on this linear model, we get the same p-value, 0.02486. Remember that in the ANOVA framework, we're always comparing two models, a full model and a simple model, or a reduced model. The full model has two categories, two parameters, b0 and b1. B0, this intercept term, very much like the intercept in a simple linear regression, a parameter that will be fit to minimize these residual sum squares, just multiplied by a column vector. And B1 is multiplied here by the first time, for the first time we'll see what's called a dummy variable. A is one category, right? And so if a data point is associated with category A, it's a 0, otherwise it's a 1. Right, so B1 discriminates A by B, and the way that R puts this in the model is to assign this column vector with either 0s or 1s. How do I know that this is what R is doing? When I call the ANOVA here, I say x equals true, and it shows me the data. Right. So this column here represents what we multiply by the intercept. In this column here, categories B, right? It's 1 if it's category B, and 0 if it's category A. As we'll see in a second, we could flip that. So we could make it 1 if it's category A and 0 if it's category B. And we'll show how to flip that and what the ramifications of flipping that are in a bit. These coefficients here in the linear model, so remember these are the coefficients that will give the residual least square error fit. So we fit these parameters so that the sum squared of the residuals is minimized. We're going to see that the intercept is going to represent, in this case, the average of the A data, and the B, right? So this intercept is the B0 parameter, and we'll see in a second that's the average of the A data. And this B1 parameter here is going to turn out to be the difference in mean between the B data and the A data. And our null hypothesis is that is 0. Right? So since the null hypothesis is that this is 0, we compare this full model to the reduced model, right? And obviously what drops out with our hypothesis that this equals 0 is this. The reduced model is just this. Right? The full model, right? I can get the error associated with the full model by just using the residuals of the full model and sum squaring them up. we've seen before that when you only have one parameter like this, this parameter will equal the mean of all of the data. So to get the residuals of the reduced model, it's just the definition of the it's just xi minus x average squared, right? So the kind of numerator of the variance that we've been seeing all semester. So that's the error associated with the reduced model. We remember our formula: reduced error minus full error divided by the difference in degrees of freedom divided by the full error divided by the full degrees of freedom. So I just put all this into R, right? So I calculate the full error as the model residual squared, the reduced error as xi minus x average squared. I plug this formula in right here. Then this is going to be F distributed with degrees of freedom 1 for the difference in degrees of freedom and 7 for the degrees of freedom associated with the full model, which is n minus 1, since there was only one parameter. Sorry, n minus 2, since there was 2 parameters in the full model. Right, so this is F distributed with these degrees of freedom and making this a one-sided test, and I get this same 0.0248. So we can do this in 3 ways now. We can get this 0.0248 as our p-value by hand crunching these numbers into here. We can say t-test with the assumption of equal variance equal to true and get this 0.0248. Or of course we can just say ANOVA mylinear model, and all of these various errors and degrees of freedom show up in our ANOVA table with the appropriate p-value of 0.2048. Okay, if we look at this graphically, right, again, this first parameter, we're considering a full model, which looks like this with 2 parameters, right? So if there's 2 parameters, we have one parameter is the mean of one data set, and the second parameter is the difference in the means between the second vector and the first vector. So this first parameter is the mean of category A, and the second parameter is the difference between the mean of category A and the mean of category B. Again, the inference is going to be that difference equals 0. That's what shows up here. This is the full model. So is this a better model where you can draw separate means for the 2 categories? Or is this a better model where you only have one mean and you're looking at the residual error between the line and all of the data, right? So in this case, the errors are the difference between each one of these data points and each mean line, right? So you have one increased parameter, and then you're looking at your residuals between each one of these data points in the mean line and each one of these data points in the mean line. Do you explain more of the variance with this 2-parameter model with respect to this 1-parameter model where all the differences are just each of the data points versus the mean line? Right? And so the ANOVA asks, does the full model explain significantly more of the data than does the reduced model? And the null hypothesis is that the data is explained just as well by a model with one mean. Now, in this case, right, we can switch these parameters around, and so we can make we can make our dummy variable flip it so that the what counts as 1 in the dummy variable gets switched from the A category to the B category, and we do that with this relevel command in R. Right, so I have these categories, and I can say, actually, I want my B to be the background. So now this intercept is going to be the average of the B data. And then this is going to be the difference between the B data and the A data, and the null hypothesis that this is 0. This generates exactly the same p-value, right? It doesn't with only 2 categories. It doesn't matter what you say is the background and what you say is the difference from the background, right? So it doesn't matter whether you flip these parameters here because there's only 2. But when we get to more complicated models, it will matter more, and we'll have to think about what to set as the background and what makes the most biological sense to set as the background. And again, that command in R is relevel. So you can force R to set as the background whatever you want, and then the math will crank through when you do the ANOVA test. And again, just to compare these two, so with A as the background, then A's are zeros, and with B as the background, the B's are zeros. The parameters get flipped between the two, but the p-value comes out as exactly the same because it doesn't matter. You're measuring the difference between the two, so it doesn't matter which one you say is background and which one you say is the difference from the background. So I once gave, as an extra credit for many years, I gave in this class an extra credit to prove that B0 equals the mean of category 1, and B1 is the difference between the means, right? And so that was clearly true to me, and I saw this stated in various places, but I never actually found a proof. And so for many years, this was, and I couldn't do the proof because my linear algebra is actually fairly weak. But Brittany Smith, a number of years ago, was a student in our program, a master's student in our program, whose background in linear algebra is much stronger than mine, and she actually took on this extra credit and did this proof. So we won't go through this in detail, but we don't actually have to say that smart people tell us that B0 is mean A and B1 is the difference between the means. Brittany Smith, a number of years ago, was the smart person who proved this, and this proof is here for your reference if you'd like it.